Hello again, everybody. This is our video solution to problem 2 from Quiz 3, Fall 2023, Math 307, Linear Algebra at Cal State Fullerton. In this problem, we are asked to explain why the list that, well, man, that's not a very long list, is it? It just has a 1 in it. So we're looking at this list here, 1, and we want to explain why this list is a basis of the vector space complex numbers over the complex numbers. Oh. Okay. Oh, but there's more. But is not a basis of the vector space of the complex numbers over the real numbers. Oh, that's kind of weird. Okay, well, let's see. Let's talk this out. So, first, why is it a basis of C over C? So, to be a basis, that means that you span and are linearly independent. So, in this case, let's see. Why don't we check the linear independence first? That seems like it shouldn't be so hard to do, right? What does it mean for this list that just contains the 1 in it to be linearly independent over the complex numbers? So that would mean that the complex number 0 has a unique representation in terms of this basis. Well, let's write down some representation, right? So it would have to be, since we're working over the complex numbers, this a here is going to be from the complex numbers, and we multiply it by 1. And, right, so here a is a complex number. And we want to know, then, what does a have to be? And of course, we're working in a field. Fields are integral domains. So if you have a product equal to 0, then one of the two factors has to equal 0. Well, 1 does not equal 0, so that implies that a is equal to 0. So we've just shown that if you have any representation of 0 in terms of this basis, it must actually be this trivial representation. And so 1 is linearly independent, right? This list containing the number 1. And you'll notice here that if we'd have replaced a not as a complex number, but just said, oh, a is a real number, right? Like the same argument would have applied. So whether or not we view the complex numbers as a vector space over itself or over the real numbers, this list here is linearly independent. So that can't be the reason why it's not a basis over the real numbers. Okay, so this is linearly independent over C and R. So why don't we check the span? So what is the span of the list just containing the number 1? Well, it depends if we're talking about the complex span or the real span. So we're going to use the subscript here to distinguish, okay? And then we'll do it over the reals as well. So over the complex numbers, this is going to be all things of the form a times 1, where a is a complex number. But of course, a times 1 is just equal to a. So this is the set of all a, such that a is a complex number. Well, that's just the set of complex numbers. So what we've just shown is that the span of this given list is actually all of the complex numbers. And so the combination of knowing that it's linearly independent and knowing that it spans the complex numbers, that tells us that this list 1 is a basis for C over C. Okay, fine. So let's check the span over the real numbers. Well, again, this would be all a times 1, but now we're only allowed to multiply by real numbers. And again, a times 1 is a, so this would be all a, such that a is a real number, which is actually just the set of real numbers, which tells us that the R span is not all of C, it's just R. Okay, so R, of course, is not equal to the complex numbers, and so 1 is not a basis for C over R. Right? The linear independence works, but the span does not. Okay, so then part B says, well, fine, it's not a basis, extend it. So we know that if you have any linearly independent list, and this given list is linearly independent, we can extend it to a basis of a finite dimensional vector space. So all we need to do is find something which is not in the span of 1, and well, let's see where we go from there. So we saw that the span over R of 1 is just all the real numbers. So we need to take some complex number that is not a real number. All right, so to extend 1, we choose something, some element of the complex numbers that is not in the real numbers, right? The real numbers, because that was the R span of 1. Well, all complex numbers, what do they look like, right? Complex numbers are of the form some a plus bi, where a and b are real numbers. So the real numbers are the ones where the b is equal to 0, right? We could actually write it this way, a plus 0i, where a is in the real numbers. So we just need now to take something that isn't of this form, a plus 0i, and now the easiest one I can think of is, let's make the a 0 and make the b 1, so that we're just taking I. So let's define a new list, 1, comma, I. All right, so recall I here is this complex number that has the property that when you square it, you get -1. All right, so because I is not a real multiple of 1, we know this list is linearly independent, since I is not in the span, the R span of 1. All right, this follows from our linear dependence lemma. Right? If this was linearly dependent, then I would be in the span of 1. All right, so it's linearly independent. Now we need to show that it spans all of the complex numbers. So the span of 1 comma I, this is going to be, now of course this is the real span. This is all things of the form a times 1 plus b times I, where a and b are real numbers. And we of course can simplify, a times 1 is a, and well, b times I we just write as bi. And again, a and b are real numbers. But if we look up above, that's exactly our definition of the complex numbers. So the span of 1 and I over the reals is the complex numbers. And so this implies that 1 comma I is both linearly independent and spans, and so is an R basis, that's another way we could say this, an R basis of C. And there we go. We have extended our list to a basis. All right, everybody, we'll see you next time.